For this particular example, let's make a couple of assumptions. And I think there is, if I remember, there is a bunch of variation also on the course website. So make sure you do them all. Let's imagine that I know, I don't care about H, I know L, I know theta. Whoops. And let's imagine that there is friction on the floor, but not on the wall. So only on the floor. And the question is, given L, given theta, given M, figure out all the external forces acting on the bar. Okay, simple enough. So let's do a free body diagram. What do we have? Well, we're given the mass, so for sure we have the weight. This is a bar of length L, therefore it's right in the middle, and that's going to be our mg. Second force that comes to mind, back to chapter 5, normal force. This object is in contact with two surfaces, therefore there should be two normal forces. Let's call this one N, and this one N prime. They're obviously not the same, so make sure you give them different labels. And then no pushing, no pulling, okay. But then there's friction on the floor. So obviously static equilibrium tells us that we're going to use Fs. I don't see any keyword that says min, max, about to move or range, therefore I'm going to treat it as Fs. I cannot use mu Sn, even though mu S and mu k are given to us. Now the last part is, what is the direction of this stupid frictional force? Well, let's look at this point A. What is the tendency of point A? Obviously, if you look at all the forces and you look at the x direction, there is no way that the x direction can be in static equilibrium, because there is only one force and it's N, and it goes towards the left. So obviously Fs has to go towards the right. Another way of deducing that Fs is indeed towards the right is to look at the tendency of motion of point A. As you laid out a pen or ladder like this, tendency of A is to slip towards the left. Therefore, friction must be towards the right. Oi. Drew, I am bummed, but I have no idea why. Are they using the link that I just sent? It's the same link. This link hasn't changed. If you're in contact with them, I would try to tell them use whatever method you used 2 weeks ago. Oh, then that sounds like a connection to me. So I would go to a computer lab that has RJ45 on the cable and stay away from Wi-Fi. There may be a connection issue. Hopefully they'll drop me a mail. Thank you, Drew. So 1, 2, 3 forces. N, normal force from the wall, normal force from the floor, N prime, friction. We know it's static equilibrium, therefore we can write 3 equations. Bing, bam, boom, done. So let's apply Newton's first law in its translational form, and let's review chapter 2 and chapter 5. This will give us the usual 2 equations. Let's pick a coordinate stem for us to be able to do this, and let's pick the origin, say, at point A. We're going to have Fs minus N is equal to 0, and then N prime in Y minus Mg. So very, very trivial. No angles, everything is either vertical or horizontal. New part, sum the torques. We should expect as many terms for torques as we have the number of forces. We have 4 forces. So common mistake is people forget terms, so make sure you write them all. You will only take 10 seconds. At least you won't forget any. And then the next stage is, after you have identified how many terms you're going to have to deal with, is to identify the point about which you want to calculate all those torques. 4 forces, and 2 happens to be acting at the same point, A. Therefore, let's pick A. Because this will allow us to get rid of 2 torques. First one, second one. Oh, yo, no, Not second one, third one. All right. Let's write two metrics just to be safe. One for the torque due to N, one for the torque due to mg. This must be equal to 0k in 2D. Let me start with mg. This is negative mg, no problem. And for n is x, negative n, 0, 0. Position vector. We are calculating about point A, therefore a position vector starts at A. And for the first torque, which is a torque due to n, it needs to go all the way to point C. So the position vector that we need is AC. The length AC is known, it's L. Therefore, back to chapter 2, this one is L cosine alpha, and this one is L sin alpha. No problem. For the weight, since the weight is at the center of mass of the bar, which is homogeneous, therefore it's halfway through the length, obviously it's L over 2. Same functional form. Done. Equation 1, equation 2. Now we're ready to obtain the third equation. Whoops, hang on. I need to... There we go. So this one, first term crosses 0, second one is positive. N, L, sin alpha, K. This is the same situation as before. The negative sign that was married with N gets cancelled from the turning of the fish. And then for the other one, the first term survived, but the second cross one does not. So negative L over 2 mg cosine alpha. Obviously, only two torque terms. Therefore, we expect it to be one positive, one negative. Otherwise, it should never be equal to 0. They're both all in K. So now we can nuke the K. And we have a third equation. L shows up everywhere again. Up. Oops, wait, no. Did I nuke the wrong one? I did. Up. And done.